when you want to figure out the derivative of the function, let's say d over dx of x squared times sine x, this is equivalent to saying the derivative of the product of two functions, and for that we use the product rule. But let's try deriving the product rule. Let's try developing some intuition for it. Where does it come from? So let's take two functions. Let's take u of x and let's take v of x. Now we will just use the basic definition of limits again, and the way we will approach this is as follows. You can say that d over dx of u of x times v of x, this is equal to the limit as h goes to 0 of, put x plus h instead of x here, so that will give you u of x plus h times v of x plus h, minus, just write the original function, so u of x times v of x. All of this is being divided by h. This is just from the basic definition of the derivative. Now, this right here is really difficult, at least it seems to me now, that it's a bit difficult to resolve into the individual components being u of x, v of x, and du over dx and dv over dx. It does not seem that much apparent now. So let's try this manipulation. What I do is I just write everything just as it is. However, I add u of x plus h times v of x, and then I subtract the same thing, and notice by doing that I'm not changing this entity right here. Everything just remains the same. However, by that same thing, you see that these two have now something in common. And this is a really common tool in mathematics, and it's used a lot in writing proofs, and we're just using that technique. Now what happens is that if you just see this first thing that I've circled in blue and just write it out, you can write this entire thing as the limit as h goes to 0 of, the thing in blue is u of x plus h times v of x plus h minus u of x plus h times v of x, all of this being divided by h. And the other part to this is the part in red, and that is u of x plus h times v of x minus u of x times v of x, and all of this divided by h again. Now the limit of the sum is equal to the sum of the limits. This is something that we have established a long time before. So what this means is that I can write this as the limit as h goes to 0 of, now I'm a bit picky about writing things again and again, so let's just take u of x plus h common out. So the limit as h goes to 0 of u of x plus h times whatever remains is v of x plus h minus v of x divided by h. And similarly, for the second part, you can write as the limit as h goes to 0, and again, I'm a bit picky about writing things again and again, so let's take v of x common out. So this gives you v of x times u of x plus h minus u of x divided by h. I'm going slight over the margins, but anyways, now if you just see what we have established here, this looks like the derivative of the function v, sort of, and this thing right here looks like something in the form of the derivative of the function u. And let's try tracing that. Let's try tracing this path again. And so what I do is I write this. This is, by the way, the limit of product of two functions, so I can write it out as the product of the limits. So this, in fact, can be written as limit as h goes to 0 of u of x plus h times limit as h goes to 0 of this entire thing, so u of x plus h minus v of x plus h minus v of x, all of this divided by h. provided that this limit exists. And so that's something that comes up in the technical definition of the product rule, but never mind, we can always just assume that. And again, this is also the limit of the product. Let's write it as the product of the limits. So this just gives you limit as h goes to 0 of v of x times the limit as h goes to 0 of u of x plus h minus u of x, all of this divided by h. And now this is pretty simple. This thing right here, u of x plus h, given that u of x is a valid thing at some x equals x naught, this entire thing is just equal to u of x, since you just plug in h equals 0 and this just equals u of x. So that's the first part, u of x. And then if this limit exists, then that is equal to the derivative of v of x, so dv over dx, plus, now the limit as h goes to 0 of v of x, notice there is no h term in this limit, so it's sort of like the constant. So just write it out. This thing right here, again, similar to this one, is the derivative of the function u, so du over dx. And there you have it. By some manipulation, namely this one right here, adding and subtracting stuff, you have figured out that the derivative of the product of two functions is actually nothing, just doing the derivative once, just keeping the other one same, and doing the same thing to the other, vice versa. And that's the product rule, and that's really great. Now, let's move on to the quotient rule. And the quotient rule just is sort of an extension to the product rule. And there are two ways we can derive the quotient rule. Let me do the easier one first. So if you want to figure out the derivative of, let's say, 3x squared over sine x, that's where the quotient rule comes in handy. And in general, we want to figure out an expression of the derivative. This was over dx, by the way. So we want to figure out an expression of the derivative of u of x over v of x, of this differentiated with respect to x. We want to figure out a nice enough expression for this. If you look at it carefully, this function is actually equal to u of x times 1 over v of x. And my intention for doing this is now this quotient has become a product. And so this function really is just the product of two functions. One of them is u of x, fairly normal. The other is 1 over v of x. And since we have already derived the product rule, we can use that to our advantage. So instead of writing v of x, we would write 1 over v of x. So this would become, so u of x just remains the same. So u of x times the derivative, d over dx of 1 over vx, plus, instead of v of x, again, you put in 1 over v of x, times d ux over dx. And all the pieces of this puzzle are sorted out except for this one. And this thing right here, we use the chain rule. The chain rule. And the chain rule is fairly simple, but before that, let me just figure the other things out. This is fairly good. This is just the derivative of u with respect to x, and this thing is also sorted out. So let's move on to this bit of the puzzle. So we can write that d over dx of 1 over vx is actually nothing, just the derivative of v with respect to x times the derivative of 1 over v with respect to v. That's the chain rule. And now it's fairly easy. This thing, we know, we can figure that out. And this stuff right here, d over dv of 1 over v, is actually equal to negative 1 over v squared. Remember, this is just v to the power negative 1, and its derivative is negative 1 over v squared. Take all of this, plug it right here. So this just gives you, and that's really nice, this just gives you that d of u over v, I'm not writing x's right now, is equal to, so u of x, just write u for that. For this entire thing that was here, the d over dx of 1 over vx, for that you just plug in this. So this is dv over dx times negative 1 over v squared. All of this plus 1 over vx just remains the same, 1 over v, and this becomes du over dx. And now what just remains is just, if you see that you can take v squared common out, so you can write this as v squared in the big denominator. You can write this as v times du over dx minus this minus sign right here, minus u times dv over dx. And this is the derivative of this function. The other way we can prove the quotient rule without using the chain rule would be as follows. So this would be quite similar to what we have done for the product rule. So let's continue as follows. So we want to figure out the derivative of u of x over v of x, all of this with respect to x, of course. This can be written as limit, let me do that in a different color. So limit as h goes to 0 of u of x plus h divided by v of x plus h minus u of x divided by v of x, all of this divided by h. And you can take some things common out, so let me write limit as h goes to 0 of u of x plus h times v of x minus u of x times v of x plus h. I'm just subtracting the fractions. All of this divided by h times v of x times v of x plus h. And after doing this sort of algebraic manipulations, you need to be a bit more creative to extract out the derivatives of these functions out of this expression. And the way we will proceed with that will be, first let's see what is immediately, what part of this expression is immediately obvious. And to me, the most obvious part is that we can figure this, that we can put v of x out of here, since v of x has nothing to do with any of this thing happening here. This limit is for h tending to 0. V of x does not has a h part in it. So this you can write as 1 over v of x times the limit as h goes to 0 of all of this thing, and I'll write that later. And if you also see v of x plus h as h goes to 0, this actually tends to v of x. And so what that means is that v of x gets squared in the denominator. Now you have h remaining, and here still you need to perform the same sort of things, same sort of manipulations that you did right here. And let's just, you can try this, and the best way to do this would be if you added and subtracted, u of x and u of x multiplied by v of x. And now you can see that this thing can be put into one thing, and this stuff can be put into the other. And through this you can write u of x plus h times v of x minus u of x times v of x, the first thing right here. This is the first part, and just similar to that, you can just add to it the limit of the remaining part. So u of x times v of x minus u of x times v of x plus h, all of this being divided by h once again. And now this is quite analogous to what we did when we were figuring out the product rules proof. You can just see immediately that v of x can be factored out, so you can write this. Let me just write the entire thing once again. So 1 over v of x squared times, well, v of x is factored out, times the limit as h goes to 0 of u of x plus h minus u of x divided by h. And again, this stuff right here, again, v of x is changing, so getting v of x plus h from v of x. U of x is not, so let's just write u of x again. U of x times the limit as limit of u of x times the limit as h goes to 0 of v of x minus v of x plus h, all of this divided by h. And now final observations. Firstly, let's just write the v squared in the denominator. Again, that's a function of x, but I'm not writing the same thing again and again. And this thing right here is v. This thing is the derivative of the function u. So this is du over dx. And there you have u of x. So u of x is just okay, you can write that. This thing right here, it does not look like a derivative, but if you put in a negative sign, so if you put in a negative sign here and you reverse these signs again just to maintain the neutrality that you had, this now looks like a derivative. It's actually the negative of the derivative of the function v, so negative dv over dx. So you write dv over dx, and there is a negative sign. And notice this is the same thing as when you would have got with the quotient rule. When we derived it through the chain rule. So hopefully this video has convinced you that the product rule and the quotient rule are indeed legitimate, and they can be proved with relatively easy mathematical proof techniques. See you in the next videos.